Chapter 6, Deep Learning and Cognitive Computing. Our learning objectives. We're going to learn what deep learning is and how it's changing the world. Know the placement of deep learning with the broad family of artificial intelligence. Understand how traditional artificial neural networks work. Become familiar with the development of the learning process. Develop an understanding of the methods to shed light into the black box. Know the underlying concept of methods of deep neural networks. Become familiar with the different types of deep learning methods. Learn how recurrent neural networks, long and short-term network, become familiar with that. What is our vignette today? Fighting fraud with deep learning and artificial intelligence. The problem. Danske Bank is a Nordic universal bank with strong local roots and bridges to the rest of the world. Founded in 1871, the bank has helped people and businesses in the Nordic realizing their ambition for over 145 years. Mitigating fraud is a top priority for banks. As I mentioned, mitigating fraud is a big thing. Most businesses lose $3.5 trillion a year in fraud. The problem is pervasive across financial industries, becoming one of the most prevalent and sophisticated each month. As customers conduct more banking online, it becomes more of an issue. Old methods of identifying fraud, such as human-written rules engines, catch only a small percentage of the fraud. While false negatives end up costing money to the bank, chasing after large numbers of false positives not only costs time and money, but also blemishes the customer's trust. The bank, like many other banks, is seeing a systematic shift in customer interactions. In the past, most customers handed their transactions to the bank branch. Today, almost all interactions are digital through mobile apps, tablets, ATMs, or call centers. This provides more of a surface area for fraud to occur. The bank needed to modernize its fraud protection. It struggled with the low 40% fraud detection rate, large numbers of false alarms. So what did they do? Deep learning enhances fraud protection. The bank integrated deep learning with graphics processing unit GPUs, appliances that were so optimized for deep learning. The new software system helps the analytic team to identify potential causes for fraud while intelligently avoiding false positive. Operations decisions are shifted from users to AI systems. However, human intervention is still necessary in some cases. For example, the model can identify anomalies such as credit card purchases taking place around the world, but analysts are needed to determine whether that is a fraud or a bank customer simply making an online purchase, sent through the payment to China, and then brought the item the next day based in London. The results, they realized a 60% reduction in false positive, with the exception to reach as high as 80%. Increase true positives by 50%, forces resources of actual cases of fraud. So by using deep learning, the bank was able to save money. So what is deep learning? About a decade ago, conversing with electronic devices in the human environment would be inconceivable. Something that would have only been sci-fi. Today, however, thanks to the advancement in AI and technology, almost everyone has experienced unthinkable phenomena. You probably have already asked Siri or Google Assistant several times to dial a number for you, phone assistants to find addresses. Sometimes when you were bored in the afternoon, you may have asked Google Home, Alexa to play some music in your favorite device or TV. Upload photos, and that identifies who's in the picture. Deep learning is the newest part, and perhaps at the moment most popular member of AI, artificial intelligence, and machine learning. It's got similar to those other machine learning methods that came before. It mimics using mathematical algorithms to learn from data pretty much the same way humans do. So what's the difference in deep learning? Here's the most commonly pronounced differential characteristic of deep learning over traditional machine learning. The performance of traditional machine learning algorithms such as decision trees, support vectors, logistic regression, and neural networks rely heavily on the representative data. That is, only we provide those traditional machines algorithms that relevant and sufficient pieces of information and proper that they learn the pattern, thereby able to predict what's going on. In other words, these algorithms need human manually identify the features of this. For example, in order for you to use a decision tree to predict whether a customer will return, the market manager needs to provide the algorithm with everything such as customer social economics, characteristics, income, occupation, along with that. But the algorithm itself is not able to define social economic characteristics or extract such information, for instance, from the survey completed. While such structure human meditated machine learning approaches has been working fine for rather abstract for formal tasks, it's extremely challenging to have the approach work for some informal tasks. Identify speech recognition, since it's required. It's not straightforward, for instance, to train machine learning algorithm to accurately recognize the real meaning of a sentence spoken by a person just by manually providing it with a number of grammatic and systematic features. Accomplish this task requires deep knowledge about the world, that it's not easy to formalize and explicit what deep learning is. The development So as we can see, development of an intimate understanding of deep learning, one should learn where it fits in the big picture of all other AI family methods. A simple hierarchical relationship diagram, taxonomy, like representation, has this in it. Characterize deep learning as part of the representative learning family. So as we look on our diagram, we start with artificial intelligence on the outer layer. As we can see here, artificial intelligence, it is part of that, but we can see that knowledge-based, expert, fuzzy logic, robotics, and we get into machine learning, decision trees that help us in, representation learning, autoencoders, clusters, PCA/ICA, and then down in the center, in this particular area, we have deep learning, CNN, RNN, LSTM, and we're going to get into what these are about. The Venn diagram shows this. Highlights the difference in the steps that when we start with the basic deep learning versus machine learning algorithms. And as you can see, the machine learning is out there compared to the deep learning. And again, in this diagram, we're able to look at knowledge-based systems that we usually call, but we got notice there's always input. Then we have the manual create representation and an output. In classic machine learning, you have manual created features, mapping, and then output, generic auto-created features, mapping output, and then you have simple features, more advanced features, mapping, and then output. Again, this is how deep learning looks when we draw it out and how we get it to do it. From the methodology viewpoint, although deep learning is generally behaved to be new area of machine learning, it initially goes back to the early 1980s, just a few decades after artificial neural networks. Process development, neural networks-based systems. Although the development of AN is similar to the structured design methodologies of traditional computer-based information systems, some phases are unique or have some unique aspects. In this process described here, we assume that preliminary steps of system development, such as determining information requirements, conducting a feasibility analysis, and gaining a champion in the top management of the project. If we look at our figure, the development process of AN applications includes 9 steps. So the first step is to collect and organize format data, separate data into training, decide on network architecture, select learning algorithms, set network parameters, initialize weight, stop training, freeze networks, test, and so on. There are several parameters for tuning the network to the desired learning performance level. But of the part of the step, the initiation of the network, weight of the parameters followed the modifications. So we need to figure out how it works. The supervised learning process, inductive, that connects weight and derived from existing. Compute temporary outputs. Compare outputs with the desired target. Adjust the weight to repeat. So adjust weight. So we have our networks, compute the output. Is it what we want? Stop the learning and freeze it. If not, we keep adjusting it so we can have our process. Like any other supervised machine learning technique, neural network training is usually done by defining a performance function and optimizing that function by changing the model parameters. Usually the performance function is nothing but a measured error across it. There are several types of error measures that we can do. The training process begins by calculating output for a given set of input using some random weights and biases. Once the network output are on hand, the performance function can be computed. Difference between the actual output and the desired output are given. The objective is to minimize delta, which will be done by adjusting the network's weight. The key to change the weight and to optimize performance, the neural network is usually done with an algorithm called the statistic gradient descent, SGD, which is an iterative gradual based optimizer used for finding the minimum and the performance functions. The idea of the SGD allows the algorithm is that the derivative of performance functions, which is respect to each of what we want. Let's see. Illuminating the black box of neural networks. Complex real-world problems in a wide range of applications. Even though neural networks have proven to be superior predictors of clusters, identifiers, many problem scenarios, allows it. It is important to be able to explain the model's inner being, such as explanation offers assurance that the network has been properly trained and the behavior desired has become. There are many techniques such as have been proposed for the analysis and evaluation of trained neural networks. These techniques provide the interpretation of how neural networks does what it does specifically. Sensitivity analysis is a method of extracting the cause and effect relationship that input and outputs of the trained neural network model. In the process of performing sensitivity analysis, the trained neural network's learning capability is disabled so that the network weights are affected. And on our figure, input is varied between the means plus or minus and the user's defined number of standard deviation, while all other input variables are fixed with are represented in means or modes. The network output is computed for the users defined as a step. The process repeated for each. As a result, report the information. Deep neural networks. Until recently, most neural networks applications involve network architecture with only a few hidden layers and a limited number of neurons in each layer. Even in relative complex business applications of neural network, the number of neurons in networks is hardly exceeded a few thousand. In fact, the process capability and time limited factors the central processing unit. We hardly ever able to run networks involving more than a couple of the layers in a reasonable time. In recent development, the GPU, along with the associated programming languages that enable people to use them for data analysis purposes, has led to more advanced applications of the neural network. GPU technology has enabled us to successfully run neural networks with over 1 million neurons. The larger networks are able to go deep into the data features and extract more sophisticated patterns that could not be detected otherwise. While deep networks can handle a considerably large number of input variables, they also need relatively large number set to be trained satisfactorily. Using small data sets for training, deep neural networks lead to overfitting the model in the trained area. Input to a regular AND model allows us to have this. The feed-forward multi-layer perceptron type deep networks, the MLP deep networks, also known as deep feed-forward networks, are mostly general type of deep networks. These networks are simply large-scale neural networks that can contain many layers of neurons and handle tensor as an input, the type of characteristics of networks. Convolution neural networks, CNN, are among the most popular types of deep learning methods. CNNs are essentially variations of the MLP architecture initially designed for computer vision applications, imaging processing, video processing, text recognition. The main characteristics of the convolution networks is have at least one layer involving a common weight function instead of the general metrics. Convolution, typically shown by the symbol star sign, in a linear operation that essentially aims at extracting simple patterns, sophisticated data, for instance, in the processing and imaging. A layer containing convolution function CNN. This layer allows by the pooling. Pooling layers are in charge of consolidating the large tensors to one smaller size and reducing the number of model parameters. In the description of the MLP networks, it is said that the weight function is generally a matrix manipulation having a very large input vector, which is the case of most deep learning applications. We need a large number of weight to have this. It should be noted that almost all practical applications of convolutional network make convolution operations are used in parallel to extract various kinds of features from the data. Because of a single feature, it is hardly enough to fully describe the input for the classification and recognition of purpose. Also, as noted, that most real-world applications we have represented in the input of multidimensional that we have. Pooling. Most of the time, the common layer followed by another layer known as pooling. The purpose of the pooling layer is to consolidate the elements into the matrix. Recurrent networks, long short-term memory. Human thinking and understanding is great extent relies on context. It is crucial for us, for example, to know what particular speaker uses very sarcastic language, to fully catch jokes that he makes, or to understand the real meaning of the word. It's a nice day of fall. Without knowledge about the other words surrounding the sentence would only be guessing at the necessary knowledge of the contents. While deep learning convolution networks are specialized to process in static grid, values like the image or a matrix of word embedding, sometimes the sequence of input. Technically speaking, any network with feedback can actually be called a deep network because with the single layer, the loop created by the feedback can be thought as an MLP type of network. However, in practice, each recurrent neural network, which involves dozens of layers, each with feedback to itself or even in the previous layers, which can make that not work. Because of feedback compilations of the gradient is recurrent neural networks would be somewhat different from the general back propagation algorithm used for the MLP networks. There are two alternative approaches for computing the gradient in the RNN, namely real-time recurrent learning. However, sometimes the relative information required to perform tasks far from where it's needed. Therefore, it is quite likely that it would have already been replaced by other information. Computer framework. Advances in deep learning owe its popularity to a great extent in the advances of software and hardware. In decades, GPU has been revolutionized to support playing high-resolution video games as well as advanced games and virtual reality applications. However, GPU's huge processing potential has not been effectively utilized for the purpose other than graphics processing up to a few years ago, thanks to the library. Torch. And we're going to hopefully get into those. Torch is an open source scientific computing framework available for implementing machine learning algorithms using GPU. The Torch framework is a library based on the LAU-JIT compiled version of the popular Lua programming language. Torch adds a number of valuable features to Lua to make deep learning analysis possible. Enables support of n-dimension arrays. Their only data structure allows us to have this. Caffe, another open source language. Multiple options to be used as a high-level scripting language, including the command line Python, MATLAB's interface, deep learning. In Caffe, everything is done using text files instead of code. That is to implement networks. Generally, we need to prepare two text files with the .pro2text extension that are communication by the CAF language in Java. The first text, known as the architecture file, defines the architecture of the network file layer, which can be defined by name. While CAF supports multiple types of deep learning architecture, it's particularly known for efficient framework for image processing. TensorFlow, another open source language, originally developed and written in Python and C++. The Google Brain Group in 2000 disbelief, but it was developed into TensorFlow in 2015. TensorFlow, at the time, is the only deep learning framework that is in addition to this type of processor. Although Google has not yet made TensorFlow available to the market, it's reported that it will use that coming forward. Dino is a deep learning group out of Montreal. Dino was the first deep learning forward frameworks, but later became a source for inspiration for developers of TensorFlow. Dino and TensorFlow both pursue a similar procedure in the sense that both typical networks implementation involves two sections. The first section, computation graph, is built upon defining it, a fact that happens in the libraries. Cognitive computing. We are witnessing a significant increase in the way technology is evolving. Things that once took decades are now taking months, and things that only in sci-fi movies are becoming reality. Therefore, it's safe to say that the next decade of technology is going to allow us to have this. The interaction between human and technology will become intuitive, seamless, and perhaps transparent. Cognitive computing will have a significant role to play in this transformation. Generally speaking, cognitive computing refers to computing systems that mathematically models allow us to have. According to the Cognitive Computing Consortium, cognitive computing makes a new class of problems computable. It addresses highly complex situations that are characterized by ambiguity and uncertainty. In other words, it handles the kind of problems that are thought to be solvable by human ingenuity in today's dynamic information. And as we can see in the diagram, cognitive computing is taking structured data, unstructured, complex, and AI, and coming up with solutions. It allows us to have everything that was going on in it. How does it work? As one would guess from the name, cognitive computing works much like a human thought processor, a reasoning mechanism, and cognitive. Cutting-edge computation systems can find synthesize data from various information sources, ways, context, and so on. Using computers to solve these issues, it allows us to put everything together. It becomes adaptive, interactive, and iterative, and contextual. How is it different from AI? Cognitive computing is often used interchangeably with AI, the umbrella term used for technology that relies on data science methods, computation, but there are differences between the two terms which can largely be found within their purpose of application. AI technologies include, but are not limited to, machine learning, neural computation, NLP, and most recently, deep learning. With AI, especially in machine languages, data are fed into the algorithms and processes so that the systems learn variables and understand what's going on. Based on that, it allows us to do it, to come up with the results. Technologies used, machine learning, neural languages, and as you can see in the diagram here on the right, artificial intelligence uses this characteristics. Find hidden patterns in data sources, automate complex, and as you can see. As you can see, differences in AI and cognitive computing. This is expected because cognitive computing is often characterized as a subcomponent of AI. IBM Watson was developed in the late 1940s by IBM. And as it started to think, it started to play. One of the first times of AI took place was on May 11th, 1997, when the IBM computer called Deep Blue played chess against the Grandmaster. After 6 matches, 2 wins for Deep Blue, 1 for the champion, 3 draws. The match lasted several days. It showed that for the first time that cognitive thinking was possible based on what was happening. In 2011, it played Jeopardy and won at Jeopardy. So cognitive is what we're up to. All right, some highlights. We looked at deep learning is among the latest trends in AI with the greatest expectation. The goal of deep learning is similar to those of that. Deep learning belongs in the representation of learning within AI. Recent emergence of this. Let's see what else. Our homework for the week. Your assignment, discussion questions 1 through 5, exercise 4. Your discussion question, list briefly describe the 9-step process. Remember, please have your work turned in by Wednesday. Thank you.